Welcome back to ECE 441A, 541A. This is the week of exam number 2, and you have 2 homework sets, so 2 is popular this morning. Exam number 2 is Friday. Homework number 4 is today due, and homework number 5 is due on Wednesday. And you should have most of the material to work those, if not all, but we will cover more Routh array material today just to give you experience with that. Exam number 2, topic-wise, you need to know about the state transition matrix, sensitivity, performance specifications, and how those relate to S-plane pole locations. You need to be able to calculate steady-state error and define it maybe as R minus Y and maybe not as a particular or a physical location in your block diagram. And obviously, you will need to be able to do the Routh-Hurwitz criterion for stability. The week following on a Friday is the homecoming weekend, and there will be no class on the 28th of October. Lab number 2 is due the following Monday, and you should refer to your graded lab number 1 to make sure that you're using the correct G of S, or you can fairly quickly in lab number 2 rerun lab number 1 for the data and collect that data and find your G of S that way. What I want to do today is go over several of the cases, if not all of the cases, that arise or can arise when you're performing the Routh array. One is when we have all of our left column elements being non-zero. Another case is when we have a 0 in the left column element and we have non-zero entries in that same row. We replace that 0 with an epsilon and continue to build our Routh array. And then we'll talk about or work through an example where we have an all-zero row, or a couple of examples. And when we have an all-zero row, that means that we have root symmetry with respect to the origin. And there you can start to visualize how are the different ways you can have symmetry of the poles or the roots relative to the origin when you have 2 poles, 4 poles, etc. And if we have time, we'll look at Routh array with an adjustable parameter, but if we don't have time, I may post some material on that, and that will be helpful for the exam. As a reminder of notation, we're labeling the coefficients to have the same subscript as the power of S, meaning a sub n goes with s to the n, and we just keep going, and then a sub 0 is the coefficient associated with s to the 0, or a sub 0 is our constant coefficient. We can now use those coefficients to build up our Routh array, and actually we can populate the first 2 rows of our Routh array based on the polynomial that we're given. And we start with the highest powered coefficient and jump over subsequent coefficients or powers of s to build the first row, and the second row then starts with the coefficient that's 1 order less than the highest, and we then keep building or populating the second row by jumping over powers of s. And if we've labeled then as having an s to the n power polynomial, we have the a in the first 2 rows with all of those coefficients in our original polynomial. Subsequent rows have to be constructed or built. They can't automatically be filled in from the given coefficients of your beginning polynomial. And if we keep going from s to the n all the way down to the s to the 0, you can see something maybe convenient happening at the very bottom. If we now have S2's row corresponding to U sub 2 and U sub 0, and we've calculated the S1 row, which will only have 1 coefficient because that coefficient corresponds to S, and then plus, you don't have anything with a coefficient of S to the minus 1, If we look to then compute u sub 0 in the bottom row of s to the 0, we have v1 times u sub 0 minus u2 times nothing, or 0, and then we divide that by v1. So we have v1 u0 divided by v1. The v1s cancel, and we're left with u sub 0. So that just sort of pops down automatically, in a sense, without having to formally compute that value in our s to the 0 row. And outside, that may be hard for me to explain, but similar popping down or inserting of coefficients happens further out in the top far right rows as you are basically dividing by what you're multiplying by at the appropriate spot. We finished last time with this, let's say, standard monic second-order polynomial. It's monic, meaning the leading coefficient of the s squared polynomial term is 1, and then we really just have two non-zero terms, a sub 1 and a sub 0. Well, if they are non-zero, we can continue with building the Routh array. If one of those was 0 or missing, what could you say about the roots of that second-order polynomial? We know they're not in the left half plane, don't we? So if we have missing coefficients, we can immediately stop unless, and that's not going to be the case on the exam, I'm going to ask you, where are these roots? I'm not going to be so trivial as to request you to just look for coefficients that are missing. Maybe. Maybe not. Maybe I'll surprise you. But in this particular second order monic, we have 1 a sub 0 in the top row. We have a sub 1 in the second row, or the s to the 1 row. And realizing what we talked about in the goal portion of today's class, b sub 1 is a1 times a sub 0 minus 0 divided by a sub 1, and that allows this a sub 0 to just quickly move down into the bottom row. And if we want this polynomial to be stable, what does that mean? Or what does that require of this information contained in the Routh array? We don't want any sign changes in the left column. And we're starting with a positive value of 1 since we normalized that coefficient to be monic. So 1 is positive. If we want stability, then we need a1 to be bigger than 0 and a sub 0 to be bigger than 0. And that was actually the necessary condition in the Hurwitz test. And in this case, for a monic second order, that's also a sufficient condition. So just having those coefficients present and positive allows you to conclude for a second order, and only a monic second order, that you do have stable or poles in the left half plane. Or in this case, the Hurwitz test is sufficient for second-order polynomials. That was sort of a review. Let's now look at a second example of creating the Routh array. And here, let's say that we have a polynomial that's fourth order, s to the fourth plus 5s cubed plus 40s squared plus 180s plus 144. And what do you do right off the bat if you're given a polynomial and asked to determine are all of the roots of that polynomial in the left half plane? You want to see if they're all present and positive. And here what may happen is I might have an s to the fourth and just not even write down the s cubed, and I jump to plus 40s squared. And if you're not paying real close attention, you sometimes can miss missing coefficients that way. just as a heads up. So pay attention and just count. 4, 3, just count down like you're going to blast off, and you will be blasting off after the exam on Friday. So here we have all the coefficients are present and positive, or in terms of the Hurwitz test, it passes both of those, and what does that mean? That really doesn't tell us that much information. It just means that the test didn't fail, or we can't conclude immediately anything about the location of those roots just yet. So let's now build up our Routh array. And we start with 1, then we jump over and get to the s squared to get 40, and then we jump over the s1 and go to the constant and get 144. The second row is now 5 and 180. And that's all we can write down in our Routh array from the given polynomial. Now everything beyond that or below that has to be computed. And if we now wanted to find b sub 1, I'm going to do that over here, what is that equal to? What are we working with to find all of these missing elements in the Routh array? The previous 2 rows, and then we're only working with the previous 2 rows, and what else if I want this leftmost entry in the second row, what am I doing with the top 2 rows, or the 2 rows preceding that? We're always working with the left column, and then we simply use the column to the right of the element that we're trying to find. And in this case, we then have 5 times 40 minus 1 times 180, and I hope it's clear where those are coming from. And then we divide that by 5. Or we have 200 minus 180, 20 divided by 5, that's 4, so we can now simply write down, and we wouldn't have to label that as b sub 1, you can just put a 4 in that location, that's fine. But I'm trying to show you where these are coming from. What about the b sub 2 entry? We're still working with the 1 and 5, and we work with the 1 column to the right, and this is that falling down scenario or dropping down scenario that I was referring to earlier. We have 5 times 144 minus 1 times nothing, so we have 5 times 144 divided by 5, so that this actually sort of falls down immediately into that location. Now to generate the S1 value, let's say that's now C1, that's 4 times 180 minus 5 times 144 all over 4. And what's that? 400 and 320, that's 720. 5 times 144, that's a little more involved, but that's also 720. We end up with 0 for C sub 1. And how many terms do we want in that row, in the S1 row? How many elements should be in that row? 1. So this is actually an all-0 row. And we can't continue with a 0 sitting there. This is now in our formulation. We now have to create or work with how to replace that all-0 row with another technique, and the technique involves the auxiliary equation. The auxiliary equation is formed from the row just above the all-0 row, And once we have the auxiliary equation, we differentiate it once, and then that result is how we will populate that all zero row. Let me try to write that down. So we have this auxiliary equation. And I'll just say that that's A of S to give us something to refer to. That comes from the row just above the all zero row, and we have 4, 144. And it's nice, I think, to have this bookkeeping on the left, because now I know that very first coefficient is associated with an S squared. It's the coefficient of S squared. My auxiliary polynomial then is 4S squared plus 144S. Is that right? No. What's that 144 corresponding to? We're jumping over, aren't we, coefficients. So we start with an S squared. We jump over the S1, and that 144 is then associated with the coefficient of S to the 0. I tried to make that mistake to make a point, but maybe I made it so quickly. I really didn't want you focusing on that error. But this auxiliary equation is from the S squared row, which is immediately above, and now we differentiate that auxiliary equation with respect to S, giving us 8S, and now we populate or use that polynomial to populate the all zero row. So we're looking for now a way to fill in the S1 row. The S1 row should have a coefficient associated with the S, and it's not going to have anything after that. And that allows us then to replace this all zero row with an 8. And what goes in the S0 row? That's that sliding down again, isn't it? This particular is 8 times 144 minus nothing over 8, or it's 144. And now we need to look at the leftmost column and count sign changes. Do we have any sign changes? No. So what does that say? Really, all I want you to conclude from that is we have no roots in the right half plane. Or maybe I should say, just to make it clear what I mean by the right half plane, let me say no roots with positive real parts. And that's the strict right half plane. That's not including the imaginary axis. But whenever you have an all zero row, that should just raise a flag. That should immediately make you start getting nervous, or at least thinking, oh, this is getting a little more interesting or a little more exciting. So the fact that we had no sign changes tells us we don't have anything roots in the right half plane, but there was an all zero row. And I don't care what color your flag is, but you need to make sure that that now raises a flag. Okay? Kind of impressed with my artistic. So now hopefully you'll never forget that there's a flag that just went up when you have this all zero row. Now, what that all zero row tells you is that you have symmetry with respect to the origin of your roots of that polynomial. Therefore, the system has roots that are symmetric with respect to the origin. And we can figure out how many symmetric roots we have, or how many roots are symmetric with respect to the origin, based on which row was 0. Which row was all 0? It only had one element in it, so it kind of is a boring all 0 row, but it is all 0. It was the S1 row. And that means that the symmetry actually is associated with the row one row above it. That one contains the roots that are symmetric with respect to the origin. So the symmetry is from one row above. Or that's really saying that we now have symmetry of 2 roots since one row above the S1 row is the S2 row. And if we are playing in the S-plane, how could we have symmetry with respect to the origin with 2 roots? Or if you put a mirror at the origin and you have 2 roots, one is going to be one way, one place, and the other one is going to be symmetric with respect to that root. Where could you have symmetry in the S-plane with 2 roots? You see, you could have something like that. Those are symmetric with respect to the origin. Is there another scenario? Don't just think real, think imaginary. So now we could have, whoops, just bragging on my drawing abilities. Usually dooms you. So now you have another case that's symmetric with respect to the origin. So we could have had this picture or that picture in general. In general, maybe not in this particular case. This is in general. But what did we have in this case? Which case of these general cases did we have, based on the information that we already have collected? What did the Routh array tell us? We didn't have anything in the right half plane, but the all 0 row said we had symmetry. The left picture gives us something in the right half plane, so that one can't have happened. It had to be roots on the imaginary axis. Is that clear? But in general, this would be the picture for symmetry. Yes? So now the question is, do they have to be symmetric with respect to the axis, or can they be on the diagonal? With 2 roots, they have to be on an axis. But once we get to 4, then you can have a more interesting symmetry. You could have them at 45 degrees in each of the 4 quadrants, or you could have them 4 on each of the axes. So it really depends on how many poles you have and the symmetry nature that they present themselves in. But in this case, they have to be on the axis because you only have 2. So if you had one in the first quadrant and another one in the third quadrant, 2 wouldn't give you symmetry, would it? Because you'd be missing something in the second and fourth quadrant. They would be getting there, but they wouldn't be completely symmetric if you only had 2. So in our case, we know we are concerned with the right picture, but if we go back to the S2 row, it was actually 4, and that's the coefficient of s squared. Then we step over a power of s and pick up the 144. The polynomial then is 4s squared plus 144, and we want to know what values of s satisfy that polynomial equation. And we can divide out the 4, giving us s squared plus 36, or s squared is now equal to minus 36, or s is equal to plus and minus j6. And that's consistent with the symmetry picture that we deduced or deducted that had to be the case for this particular example. If you would have had one sign change and symmetry with respect to the origin, then you would have had the left picture. Is that clear? Let's look at another example. Question? So now the question was, is this system, if that was a denominator polynomial, is this system that we just worked on considered stable or unstable? The textbooks usually say it's marginally stable, which means that if you had something excited initially, it would just sit there and shake at 6 radians per second. But I don't like that, because if somebody was cute and started shaking it themselves with an external input at exactly 6, then you're going to have a t sine of 6t and a t cosine of 6t, and that's going to go unbounded. I prefer to stay away from even roots on the imaginary axis as far as a practical system. But if you were designing an oscillator, maybe this would be good. Then you would have this oscillator that you get it started and it just sits there and shakes. I don't know if that's 6 radians minus, but that is 6 radians per second. Is that, I kind of stay away from the term marginal, but yes, it's on this border between something in the right half plane and something in the left, but it really only behaves properly if it is excited with initial conditions. But if you start shaking it at exactly that resonant frequency or that frequency, you'll get unbounded results. And I forget now what I was reading, but apparently, oh, maybe it was the textbook. Imagine that. They had a building that actually was, they had to shut it down because they had an aerobics class on the 11th floor, and they hit the natural frequency of the building, and the building started shaking. And it wouldn't stop shaking, and they go, let's stop aerobics and let's exit. They shut the building down for 2 days, I think. Check your textbook and see if I'm being truthful in my shaking or in my memory. But you can start to, and the Tacoma Narrows Bridge, that's a classic example. You can look that up on YouTube, and the wind starts shaking it at its natural frequency, and it falls apart. And there's some cars on it. Luckily, I don't think anyone was hurt, but I'm sure it was frightening if you were on the bridge and it started to shake. It's not as funny or cute as shaking up here. Okay? Let's now look at it. Where were we? Number 3. So now we have delta of s is equal to s cubed minus 3s plus 2. What's Hurwitz tell us? This tells us that we already have problems because we're missing an s squared term. One of those coefficients is missing. So it fails the necessary test, and so we do have an unstable polynomial. But that's never stopped us from having fun on an exam or in class, so let's build the Routh array. Because on the exam, I probably won't just say, does this polynomial have any roots in the right half plane? Oh, it failed the Hurwitz test. Move on. 20 points. Thank you, Tharp. So that probably won't happen, and I'll say how many do you have in different locations of the plane? And then you'll have to know, do I have symmetry or some on the imaginary axis? Do I have how many on the right half plane, how many on the left half plane? Let's build the Routh array. What we start with s cubed, s squared, s1, and s0. Shaking too much up here and my tablet's misbehaving. It's thinking I want to stop the buttons. Now, how do I build this? What's in my top row? And there is our 0 in the left column and non-zero to its right. And this is the case that we use case 2, and we can now insert an epsilon to allow us to continue to build the Routh array. In this case, if we now create the next row, the S1 row, we have epsilon times minus 3 minus 1 times 2 over epsilon. And thankfully, we don't have to mess with that mess necessarily when we get the S0 row. What does it look like? Well, that's one of those drop-down immediates. That's 2 times that mess divided by the mess. The mess cancels, and we're left with 2. So the second, or the S0, drops down because of that empty location there in the S1 row. And now what do? Now we look at the left column. Bless you. And we're now looking at epsilon is positive, and it's going to 0, let's say, from the right. It's approaching 0 as a positive value. That's what I'm trying to indicate by that piece of information in parentheses. And that's important here because now we have something really small, minus 2, divided by a positive number. That something small is being dominated by the minus 2, and the epsilon is positive. What's the sign of that S1 row? Negative. What's the sign of the S2 row? Positive. We needed to make an assumption on the sign of epsilon. We made it positive, and now we go positive, positive, negative, positive. So the left column entries tell us we have positive, positive, negative, positive. And how many sign changes does that correspond to? And how many roots are in the right half plane? Equal to the number of sign changes. We have 2 roots in the right half plane. Now somebody might say, what are your roots? So we had this polynomial. Let's just go back and relive our algebra class and do some synthetic division. We had s cubed, nothing times s squared minus 3s plus 2. The 1 comes down, and we multiply that 1 times minus 2. We add those, we get minus 2. We multiply minus 2 and get 4. We add those and get 1, and we have 1 times minus 2, and that's what we were, oh, good, we found a root. We found a root was actually at minus 2. We were just checking, doing this quick synthetic division to try to determine, can we find a remainder of 0? And if we did, then we now know where one of the roots are in this third order polynomial. This now tells us, since this has a 0 remainder, that we now have a root at s equal minus 2, and the other roots are result from this being factored. And this now corresponds to s squared minus 2s plus 1. And if we combine those, we know that we now have a root at minus 2, so that gives us an s plus 2 factor. And we have a factor that's s squared minus 2s plus 1. And that can be factored. And we end up then with what we were learning as we were working through this example. We had a root at minus 2 determined from the synthetic division, and we had 2 roots at s equal plus 1. Question? So where did the negative 2 come from in the synthetic division? Out of thin air. Actually, it came because, well, we know we're looking for a root to this cubic, and we're just trying to guess some possibilities. And the coefficient, the constant coefficient was 2, and I'm thinking, how can I find something that might give me a 2? Oh, it could be a plus 2, a minus 2. So I just said, let's hope it's minus 2. And that's where that 2 came from. Yeah, it's guess. But you have your calculators, which, well, I'm just trying to remind you of what you've learned in your earlier algebra classes on synthetic division and connecting that with what we're learning now. But now you have those 3 roots. Let's look at a symmetry example. And sometimes it's nice to just build one up on your own, and then you know what you should be getting and see if what you're getting is actually bearing fruit. Suppose that we have a 0 at the origin and another 0 or root at plus 1 and another root at minus 1. And we want to know now, what's the polynomial look like? For each of these cases, what's this factor look like in our resulting polynomial? We now have s minus its root, which is at 0. And what's this one look like as a factor? That's now s minus 1, since we want that factor to give us a value of s that equals 1. So 1 minus 1 is 0. That's the factor for that one. And then what's this one's factor? That's s plus 1. We now know what delta of s is. That's s times s minus 1 times s plus 1, or that's s times s squared minus 1, which is now s cubed minus s. And let's look at the Routh array then that results from this example. How do I build it? If I keep track of my bookkeeping steps, I now have s cubed, s2, s1, s0, and I want to populate the top 2 rows. What's in my top row? Is that what I heard? 1 and minus 1. And what's in the second row? I need my s squared coefficient. I need my constant coefficient. That's an all 0 row. So now what do I do? I need to find my auxiliary equation from the row above my all zero row. My auxiliary equation is actually my original polynomial in this case, but it's now s cubed minus s. We differentiate that, 3s squared minus 1. Now we can use those to fill in these zeros. We have a 3 there, and we have a minus 1 there. And now the S1 row can be created. We have 3 times minus 1 minus 1 times minus 1 all over 3. And what's in the S0 row? That's that drop-down feature again, isn't it? This is actually minus 1. That's going to be this dropping down. And what did this expression yield as a value? We have minus 3 plus 1 minus 2 over 3. So that's minus 2/3. How many sign changes in that Routh array? Which means what? Pardon? 1 root in the right half plane. We already knew this since we cooked up this example to begin with, right? But we now know that the symmetry is relative to what set of roots, or which row was all 0. The second row, the S2 row. The S2 row was all 0, and that means how many roots are there symmetric with respect to the origin? Where's my symmetry? The S2 row was 0. Which row now yields the symmetric roots? The row above it. That's an S cubed. So now we have 3 roots that are symmetric with respect to the origin. So the S2 row being all 0 says we have, or allows us to conclude that we have 3 roots that are symmetric with respect to the origin. And that means then in general, what do we have picture-wise? We have 3 roots that are symmetric with respect to the origin. I cooked this up just so we could start to see that we maybe don't always have even numbers of symmetric roots. 1 is in the center, isn't it? We put 1 right at the origin, and then we can either go up, let's say by B, or to the right and left by A. Which case did we have? We had the one on the right because we actually came up with, from our Routh array, 1 sign change. So we had this picture on the right as our symmetry. Questions on that? Let's now look at what we could do, knowing that we can build this Routh array, and maybe we have an adjustable parameter in our polynomial. Let's say that our system has been parameterized as a numerator omega sub n squared, and we have an s plus 2 zeta omega sub n. We've parameterized it in terms of a damping ratio and a natural frequency. That's now our plant. Where are the poles of that plant? If we just said this is our open loop plant, where are the poles of that plant? The values of S that cause the denominator to vanish, right? So we have one at the origin, and we have another one at minus 2 sigma, or minus 2 zeta omega sub n. We now want to control that system by putting in a controller, and let's now build a controller with a gain, and let's say that we have a gain in parallel with that of K over S. So that, and then we will compare that output that results with our input R, and this that's in the dashed box is our controller, which is going to take this air signal and filter it by, one, pushing it through without a gain, just directly with a gain of 1, I should say, passing that through, and then adding to that the air. And what's this K over S block doing in the time domain? What would you say that controller, how is it behaving? Our controller is the combination of a 1 plus K over S. This one we could say is a proportional gain. And what is this one doing? What's 1 over S in the frequency domain? Or dividing by S? What if you multiplied by S a polynomial? If you multiplied that polynomial by S, what are you doing in the frequency domain when you multiply by S? You're differentiating, aren't you? So dividing by S, you're integrating. So this is actually an integrator, an I term. And this controller is a very good investigator. It's a private investigator. No, it's a PI, proportional and integral controller. This is a PI controller. And you can contrast that with a PID controller, where you might also have a derivative term. But in this case, the PI controller, this integral, helps us improve our steady state accuracy, or the behavior of our system in the steady state. It might eliminate errors entirely because we're integrating those errors away. So what we want to do is find the closed loop transfer function as a function of this adjustable parameter K, and adjust that gain, or find values of gain K, using the Routh array that will stabilize this system. And then we can say, oh, we can play in this region of variable K and still keep the system stable. I will probably just post a video of this so that you have it for forever. There you go. We'll pick up at that point on Wednesday.